Hi everybody, hope you're doing well. So to start here today, I think it would be a good idea for you to go back to your notes and review the topics that we were last learning about. So if you take a look at this graph here that I've sketched, we had some graphs similar to that we used to talk about absolute extrema, local extrema, and things like that. So go back through your notes on extrema and also your notes on critical numbers, and then we'll use that information as we move forward. Okay, today's lesson is called Local Extrema and the First Derivative Test. And I'm sorry, I forgot to look up the notes number. Okay, actually I just looked it up. So the last notes was notes number 30, so this is 31. And it would be called Local Extrema and the First Derivative Test. Okay, so let's take a look at this graph here. It shows a local maximum because no point is higher in the neighborhood. And let's talk about what's going on with the function f of x. So over here on the left side, f of x is increasing. To the left of the maximum, f is increasing, and to the right of the maximum, f is decreasing. Anytime a function is increasing, it has positive slopes. You could draw little tangent lines and see that their slopes are positive. So we would say that f prime of x is greater than 0. The derivative is positive if the function's increasing. And then on the right side, we would say that f prime of x is less than 0 because the slopes are negative, so the derivative is negative. And then what's happening at the critical point? Right there at that point, f prime of x is 0. We would have a horizontal tangent line. Okay, now let's take a look at the next graph. We have a critical point with a local minimum. And at that point, the derivative would be 0 because you would have a horizontal tangent line. Before that point, you see the graph is decreasing. So g, oops, I should have called the other one g prime of x. So to the left of the local minimum, g is decreasing. Therefore, g prime of x is negative. And to the right of the minimum, g is increasing. Therefore, g prime of x is greater than 0. Okay, now, we also could have a maximum or a minimum at a point where the derivative does not exist. Take these two examples. So this point here would still be a critical point, but the derivative would not exist there. H prime of x does not exist because it's pointy, not smooth. Let's look at what's happening before that point. H is increasing. That means that h prime of x would be positive, greater than 0. If a graph is increasing, its slopes are positive. And to the right, h is decreasing. So h prime of x is negative. Okay. In both cases that we saw on the left side of the screen, we have a local maximum. In one case, the derivative was 0. In the other case, the derivative did not exist. But in both cases, we have increasing function on the right, decreasing function on the left. Positive derivative on the right, negative derivative on the left. And then going back to the fourth example, m of x. Here we have a local minimum, and m prime of x would be non-existent, does not exist, because there's no derivative there at that point. And on the left, m is decreasing, so m prime of x would be negative. And on the right, m is increasing, so m prime of x would be positive. Now maybe this seems kind of obvious to you, but it's very important and foundational to what we're about to do that we understand the relationships between if a function's increasing, its derivative is positive. If a function's decreasing, its derivative is negative. If a function has a local maximum, then it changes from increasing to decreasing. If a function has a local minimum, then it changes from decreasing to increasing. Very, very, very important. Okay, here's a couple of examples. Sketch the graph of a function f of x such that f prime of x is positive. Greater than 0 means positive. For x less than 1, and f prime of x is negative for x greater than 1. Okay, so let's put x equals 1 in place. That seems to be the point where things are changing. And what we want is the derivative is positive, then the derivative is negative. If the derivative is positive, f is increasing, and if the derivative is negative, f is decreasing. So what we want to show is a function that increases and then decreases. We could do this, increasing and then decreasing. There's more than one way to do it, but that is one way. Number 2. Sketch the graph of a function f of x such that f prime of x makes the sign transitions positive, negative, positive, negative. That tells us that the derivative is greater than 0, less than 0, greater than 0, less than 0. And that tells us that f of x is increasing, then decreasing, then increasing, then decreasing. Okay, so let's draw something like that. Let's draw a function that increases, then decreases, then increases, then decreases. There we go. That's an example. All right. Now we get to the main point of today's lesson, and that is how to find local extrema. Remember, in the past, we had how to find absolute extrema, and that process was find the critical points, find their y-coordinates, find the y-coordinates of the endpoints, and then see which one's the biggest and which one's the smallest. Now we have a process for how to find local extrema, and it is called the first derivative test. It's called the first derivative test because it involves the first derivative. Step 1, find the critical points. And remember, critical points are x values where the derivative is 0 or does not exist. If you look back at the first thing we did here today, we had our local maxima, which occurred at points where the derivative is 0 or does not exist. And our local minima occurred at points where the derivative equals 0 or does not exist. So that's why we have to find critical points. Okay. Next, form intervals around the critical points. Intervals. Basically, we want to know what's happening to the left and what's happening to the right. Remember in the first slide, we looked at it's increasing on the left, it's decreasing on the right, or it's decreasing on the left, it's increasing on the right. We need to find out what's going on, increasing or decreasing on the left or the right, so that's what the intervals are for. Step 3, test each interval to see if the derivative is positive or negative. Because if the derivative is positive, the function's increasing. If the derivative is negative, the function's decreasing. Look at the sign changes to determine if the critical number is a local max or min. And just so you know, it might be neither. So, if you see that the derivative changes from positive to negative, that means the function went up and then it went down, so you have a local maximum. If you see that the derivative changes from negative to positive, that means the graph went down and then went back up, and you have a local minimum. But if you see that the derivative went from positive to positive, it was going up, and then it was going up again, you don't have a local max or min. Or if it went from negative to negative, same thing. If the derivative went from negative to negative, decreasing, then decreasing some more, you don't have a local max or min. So just if you see a sign change. Okay, so that process is called the first derivative test. Now, later we learned something called the second derivative test. The second derivative test and the first derivative test do the exact same thing, but they do it in a different way. The first derivative test uses the first derivative, and the second derivative test uses the second derivative. Let's do an example. Find the critical points and the intervals on which the function is increasing or decreasing. Use the first derivative test to determine whether each critical point is a local minimum or maximum or neither. Okay, to find the critical points, we need to find where the derivative equals 0 or does not exist. So let's find the derivative, and that would be 3x squared minus 12x. Minus 12, sorry, 3x squared minus 12. Okay, there's no place where that does not exist because that's just a polynomial expression. So let's find where that equals 0. We could factor out the 3. We could divide both sides by 3. We could factor the quadratic expression, or we could just add 4 to both sides and then square root. And be sure when you square root to put plus or minus. So plus or minus 2, those are the critical points. Okay, so it said find the critical points, so we did that part. Next it says, and the intervals on which the function is increasing or decreasing. Okay, so what we do is we go from negative infinity to our lowest critical point, negative 2, and then we go from negative 2 to the next critical point, 2, and then we go from 2 to infinity. Those are the intervals. Okay, so we found the intervals. Now, we need to test a number into each interval to see what the derivative is doing. So let's test x equals negative 3. Let's test x equals 0. And let's test x equals 3. And to test it means to plug it into the derivative and see if we get a positive or a negative. So f prime of x. If x is negative 3, and you substitute that into the derivative, you could substitute it into there, or you could substitute it into the factored form. Negative 3 squared is 9. 9 minus 4 is 5. 5 times 3 is 15. That's positive. Let's move on and test 0. 0 squared is 0. Minus 4 is negative. Times 3 is negative. The derivative is negative. Let's test 3. 3 squared is 9, minus 4 is 5, times 3 is 15. That's positive. So now we know the intervals on which the function is increasing and decreasing. The function is increasing when the derivative is positive and decreasing when the derivative is negative. So it goes from increasing to decreasing to increasing. So do we have any local maxima or minima? Just picture this. Your function's going up, then going down, then going up. Yeah, when it changes from increasing to decreasing, you have a local max. Local max at x equals negative 2. And when it changes from decreasing to increasing, you have a local min. Local min at x equals 2. We don't actually have to see the graph. We just need to know these changes. Derivative changes from plus to minus. That means function changes from increasing to decreasing. That means you have a maximum. Derivative changes from negative to positive. That means function changes from decreasing to increasing. That means you have a local minimum. Now, at times they might ask you for the ordered pairs for the extrema. So instead of just giving x equals 2 or x equals -2, you could find the y-coordinates of the points by substituting the x-coordinates into the original function, and then you could give ordered pairs. Okay, let's try this one. Same thing, find the critical points and the intervals on which the function is increasing or decreasing. Use the first derivative test to determine whether each critical point is a local minimum or maximum. Okay, so let's find the derivative, and that would be 6x squared. There's nowhere where that's not defined, so let's just see where it equals 0. Divide both sides by 6, square root, and we get plus or minus 0, but that's just 0. So this is our critical point. We just have one critical point, x equals 0. Now we make intervals. So we have the interval from -infinity to 0 and the interval from 0 to infinity. Now we want to know what the derivative is doing in each interval. So let's pick a number in each interval. Suppose we pick x equals -1 and we pick x equals 1. Now we're going to see what the derivative is doing. So if we plug -1 into the derivative, we have -1 squared, which is 1, times 6, which is 6, and that's positive. If we plug +1 into the derivative, we have +1 squared, which is 1, times 6, which is 6, and that's positive. So notice there is no sign change. No sign change. So what's the function doing? The function is just going from increasing to increasing. That's not a minimum, that's not a maximum, it's neither. In fact, if you think about what y equals 2x cubed would look like, just a basic cubic function, stretched out twice as tall as the parent function would be, you see it's increasing and increasing again. So what happens, if I make it a little bit more obvious, is it goes momentarily flat and then it goes up again. So that moment where it's momentarily flat is where the derivative equals 0, but it doesn't turn back down and go down. It doesn't turn back around. Okay, let's see what else we have. I'm not going to go through every single example because that would make the video way too long. I think what I'll do actually is just stop the video now, and then I'll start a second video where I do maybe examples 5 and 6. And then I'm going to give you a brief homework assignment which has a few problems to try. Okay, thanks everybody.